associate professor at National Higher French Institute of Aeronautics and Space. He's a very active guy in mechanical behavior of metallic materials and high temperature ones with strong mechanical experimental skills. And of course, the link with simulation aspects. So his presentation today is about creep and fatigue of nickel-based superalloy processed by LPBF and laser metal deposition. Please, Mr. Cormier, start the show.
Thanks, Guillaume, for the nice introduction. So I will share my slide. Oh, I think it's not this one. Just a moment. Okay, can you see my slides?
Yes.
Yes.
Okay, great. So, so today my talk, being in an engineering school like ISA and SMA, naturally we are working on applications for aerospace. And today my talk will be mainly focused on, let's say, mechanical properties of high temperature materials processed by additive manufacturing, more specifically powder bed fusion and laser metal deposition. And my talk will be focused on different kind of alloys, ranging from 718, WASP alloy, RINI 65, and CMS 64. So to start with the context of this study, we deal with materials which are typically used for the hot sections of gas turbines, so not only for aero engines, but only for industrial gas turbines, or for sometimes petrochemical applications or turbochargers for cars, Formula Ones. But we mainly focus today on applications for jet engines, helicopter turboshaft engines. And those alloys are used for the manufacturing of discs, seal rings, and airfoils, blades of the hot section. So for the HP sections, low pressure turbine sections, but also for the very last stages of the compressors here. So here you have the typical temperature of during service of those components for this, ranging from 400 C in the bore sections up to 700 C for the rim sections. And regarding airfoils, especially HP sections, we are ranging from 500 to 700 for the blade roots, up to 1150 C at the blade tips. So the key questions are we able to replace conventionally those components? Are we able to process them by additive manufacturing? And the subsequent questions are what would be the tensile properties, creep properties, fatigue properties, and the anisotropy and oxidation of AM processed materials. In fact, for a flying object, you have to consider that before being under the wing, those components have to be certified. And that's a really critical issue. And FAA and EASA are imposing some criteria to be able to use those kind of materials for jet engines. And we have to understand what are the challenges in terms of processing so as to use AM processed materials. So there are already some components which are used. So typically fuel injectors are processed by AM techniques for different original engine makers. But we need to know if we can introduce in a reliable way additive manufacturing for this class of material. Another question, which is slightly different, is can we use additive manufacturing as a reliable means for repair purposes? And I will end my talk regarding this. So first of all, I'd like to start with some monotonic mechanical properties of the most widely used alloy, super alloy in that field, so alloy 718 or Inconel 718. This alloy is typically typically for nearly 50% of the weight of an engine. And first of all, I'd like to make a comparison between, let's say state-of-the-art materials, so conventionally forged alloy, a cast and wrought with, let's say, a fine grain microstructure ranging from 15 to 25 microns, with a given level of strengthening provided by intermetallic precipitates, so gamma prime, gamma double prime mainly, and powder bed fusion laser alloy, 718, where you can see a comparison of the typical microstructure. So typical equiax microstructure with several twin boundaries here in this kind of microstructure, while for the as-built SLM material, you have this kind of typical microstructure, and at a lower scale, we can recognize a cellular type microstructure. So all this work has been done within the framework of the PhD thesis of Sassi Perian, in the framework of a collaboration with the University of Tours. And what we did also within this context, we wanted to use, let's say, optimized microstructure using heaping. So we did heaped with an integrated heaped plus solution heat treatment, followed by aging to trigger the precipitation of the strengthening phases. So typically gamma prime, gamma double prime. Now, let's now move on the properties. First of all, tensile properties at room temperature at 650 C. I'm just giving some typical curves. In fact, we have several results, at least 5 to 10 results each time. So you just have to take the picture, but we have several results to show this. So in each cases, the green curve accounts for the cast and wrought material, conventional strain, conventional stress plots. And we can see that the as-built microstructure has a ductility of nearly 2% at each temperature. And something which is very interesting is to see that the heaped material with optimized heaping cycles provides outstanding properties, very comparable to the cast and wrought material at high temperature, and surpassing the cast and wrought material at lower temperature. Something I'd like to mention also, which is well understood now in the literature, is that even in the as-built state, we can see that we have quite high properties, and we come back on this later in this presentation, with a typical yield stress of nearly 900 MPa, despite the absence of any strengthening precipitates. And those quite high tensile properties in terms of yield stress are mainly coming from the very high dislocation density we have in the as-built state. And this is something we can already understand with this kind of observation here, where you can see lots of variation in contrast at the grain scale, being an indication of the high dislocation density we have. So, okay. From a failure point of view, we can see linked to this lack of ductility. We can see that crack initiation is mainly coming from lack of fusion and pores remaining in the as-built material, while in the heaped state, we don't have any more, or very few of them at the end. If we move now to creep properties, we have been testing also creep properties at 650 C, 800 MPa, 750 MPa, same time scale here, in which we compare the powder bed fusion 718, so the red curves here, and two type of forging, hydraulic pressed forge 718, screw pressed forge 718, so the processes which are used for the processing of HP disc and LP rings for aero engines. What we can see in both cases is that the curves are pretty the same in terms of primary, secondary creep stage, or up to 1 to 2% creep strain. Still, there is a very pronounced lack of ductility, which prevents the alloy of being used in that state for such kind of high strength, high integrity components. And the main reason behind that is that you will see later on, even in the heat state, we have always some remaining pores, small ones, where we have probably gas trapped within the pores, but they are serving as crack initiation site, and they are limiting overall the ductility of the alloy. Moreover, we have been able to observe crack initiation at specific grain boundaries. I'm not showing this here clearly, but we understood that it is linked also to some oxides remaining at grain boundaries. And this kind of results is really typical in the literature. That's something which has already been observed 4 years ago by a Japanese team in the group of Koji Kakei at Tokyo Tech, where they compare the creep properties of vertical and horizontal specimens. I forgot to mention that the results we obtained within the framework of the Sassiperian thesis. We had a little bit of anisotropy, but the trend was almost the same for both vertical and horizontal specimens. And if we come back to the very pioneering work coming from Oak Ridge National Lab, so the group of Michael Kirka and Suresh Babu, they made the choice quite rapidly to work with EBM processing. And they observed that for specimens matching along the build direction, so the microstructure for this kind of process leads to very columnar type microstructure. They observe very high properties, comparable or sometimes even surpassing the creep properties of cast and wrought material. But when they are loading along transverse direction, they come back to the same problem of debit in ductility. This kind of anisotropy in creep strengths, which has been found for both PBF-E but also PBF-L processing, is not something specific to this class of processing. I mean, it's not specific to AM, that's really specific to the columnar type microstructure or directional type microstructure we have, in which we know that if we don't have any particles or something specific that will strengthen the grain boundary, we have a lack of ductility overall, and that's something which is well known in the literature for directionally solidified cast superalloys. Okay, so yesterday you had also the talk of Sandra regarding the development of residual stresses in situ during wire printing on the salsa line at ILL. We are working at ENSMA to understand the microstructural evolutions and the mechanical properties of this kind of process. So this is a collaboration with ILL and also Fraunhofer, Dresden. And first of all, here you have a typical microstructure in the as-built state. So this is an EBSD map with an index quality observation map. And here, backscattered imaging mode, in which in the as-built state, we can observe the dendritic type structure, and all the white particles or black ones here in IQ mode corresponds to laugh phases. And that's something which is known in the literature to be detrimental to the properties. We will see that's not really obvious afterwards, but that's something usually considered to be detrimental, especially for toughness. So first of all, what we did here, we tried to develop heat treatments to be able to get rid of this kind of phases. And here you have a typical evolutions of the laugh phase content, starting from 7–8% in the as-built state. And we can see a progressive decrease of the laugh content, increasing the solution treatment temperature. And we cannot go in excess of 1200 C, the problem being that we will reach afterwards incipient melting. So in the following slides, I will show you that we are using solution treated specimens to understand the properties, with the solution treatment being 1 hour at 1200 C. Then we have been doing EBSD maps. So that's a sketch of a wall from which we have been removing tensile specimens. And here you have an EBSD map in the as-built state and after solution treatment along the build direction, which is horizontal in that case. And we can see that we have very impressive texture in this material. So we can recognize here one wire, another wire, and each interlayer, you have a little bit of recrystallization coming from the deposition of the N+1 wire. And when we do further solution treatment, we can see an even greater texture. So this is something, I'm not showing here the texture map from which we could be able to understand better the texture, but that's very obvious from the BSD map. So with this, we have been doing tensile tests along horizontal direction, vertical direction, so build direction, and also at 45 degrees. And that's what I'm showing here. So all the tensile tests have been done at the same strain rate, 5×10⁻⁴ per second, at room temperature, 450, 650, 750, 850. So I will first start with the room temperature test. So we have here in blue the as-built state for all the orientation, solution treated state, and then solution treated plus aging, a typical aeronautic aging to trigger the precipitation of gamma prime and gamma double prime precipitate. Probably not the optimal one for this kind of process, but we know that we are improving the properties. So what is really impressive, first of all, is to see that in the as-built state, we have quite high yield stress in comparison to the solution treated material, in which we have yield stresses of nearly 300, 350 MPa, which are really typical of solution treated cast and wrought 718. So no surprise on this. So it means that we have an increase of properties provided by the non-negligible fraction of LAF phases. And then when we introduce the precipitation of gamma prime and gamma double prime, we can see another increase, which was expected from the beginning. Still, the yield stress here is quite low in comparison to a forged alloy due to the very, very large grain size. You have to keep in mind that typically we have columnar grains and then a grain size in this direction, which is typically in the order of something like 100 to 200 microns and very, very low neighboring misorientation. We did the same at 650, so very busy chart. Same trend overall. And something which was interesting, we also did direct aging on the as-built material. So starting from a blue curve, we introduce the aeronautic aging. And what you can see is that we are even surpassing the solution treated plus age material. So meaning that here for the purple curve, we are combining strengthening coming from LAF phases, gamma prime plus gamma double prime. So that's something very important we understood. And we are still working on to fully understand. So from those experiments, we saw no specific detrimental effect of LAF phases on tensile properties. We have overall a very weak anisotropy in inelastic behavior. I'm not speaking about the elastic part in which we have anisotropy, as expected from the very large grain size. And we can see that LAF phases are providing a strengthening. And more recently, we did some tests at 750C. They are really important, especially because we are trying to understand the peaks evolution during either in situ printing or post-built heat treatments. So we did those experiments at 750C, mainly testing along horizontal direction in the as-built state. And something I want you to pay attention is the variable here is the soak time at 750C before starting the tensile tests. And so here, look at this. We have 5 minutes soak time for vertical direction. 5 minutes, sorry, yes. We tested immediately the material here after reaching 750C. Half an hour, 2 hours, and 3.5 hours for the red curve. So what you can see is that we have an increase of the yield stress and a progressive decrease of the ductility. And the increase in yield stress is directly coming from, and that's a picture I took last week, is directly coming from the in situ precipitation during the soak time before starting the test. While the decrease in ductility we suspect to have environmental embrittlement of grain boundary. So it means that we need to take great care on the testing procedure if we want to characterize the properties of this class of alloy, which is unstable in this temperature range. Okay, so after those monotonic properties, I want to move to something really important when we need to consider certification rules of components for aero engines, so the fatigue properties especially. According to the literature, focusing on AM material, I'm still considering the case of 718, which is a weldable alloy. I just want to summarize rapidly that most of the issues are coming from processing defects. So typically lack of fusions, pores, and as long as we have this kind of defects inside the materials, the anisotropy, the way the specimen is built is not really important. I mean, in terms of texture, for example. So if we want to be able to characterize intrinsically the properties of this class of material, we need to get rid of defects. That's also something interesting for wire deposition being a process in which we know that we have a lower porosity in terms of volume fraction and or size. So we have been working in collaboration with G Additive in the US and with a colleague from the University of Arizona, working on Rini 65. So an alloy very difficult to print with a very high volume fraction of gamma prime precipitates. So here you can have an idea of the precipitation state. So you have a typically 40–45% volume fraction of gamma prime precipitate. A little bit of borides and carbides also. And what we did, so this is a DMLM process, so which is a G powder bed fusion type process. And we have been studying the alloy along vertical, horizontal direction and using combined solution treatments plus HIP. So they are optimized processes to be able to get rid of porosity. We have typically less than 0.1% pores. I cannot give all the details on this. So what you can see in supersolvous treated state, we have microstructure very, very similar to a cast and wrought material with several twins. And something very interesting is that we are able to reach a grain size, which is very difficult to reach with a conventionally processed cast and wrought material, meaning for a cast and wrought material, you have usually 5 to 20 microns grain sizes. And then when you do supersolvous heat treatment, you have grain sizes of typically 200 to 300 microns. So it's very difficult to have an intermediate grain size in which you can optimize both creep and fatigue properties. So we have been able to reach such kind of grain size with this process, thanks to very nanoscale contaminations at grain boundaries, while we have typicals PBF-L microstructure in the subsolvous state. Be careful here, we have this class of precipitate, and at a lower scale, we have a second class of tertiary precipitates. We did tensile tests, so once again, strong focus at 650 C, because that's a condition at which we will benchmark the alloy with 718. Same kind of strain rate, so we can see a sensitivity which is mainly linked to the HIP treatment, which has been introduced. Very weak sensitivity to the direction along which we are doing the tensile test. And then when we did fatigue test, so this is an SN diagram, half strain range as a function of the number of cycle to failure, Those tests have been performed here at P prime with a frequency of 0.5 Hertz, sinusoidal waveform, fully reversed conditions. And here you can see all the data points we have for the 4 batches of specimens. Something which is really impressive is that we see almost no anisotropy and one single trend, which is almost the same as the cast and wrought material, meaning that this kind of process can be introduced. From the point of view of crack initiation, we observe almost the same crack initiation as for the cast and wrought material, meaning surface crack initiation at this temperature. That's really typical. We have crack initiation at twin boundaries assisted by oxidation. And very occasionally, we obtained crack initiation from an internal site at a particle, non-metallic particle, being typically an alumina type particle coming from the processing of the powders. Most probably, I don't have all the details from G on this. So that's something very interesting in terms of the possibility of introducing this class of material for high integrity components. Still, we need the heaping stage. But there is no other possibilities. Now I'd like to move to something really fancy. We are working in collaboration with the colleagues of the University of Erlangen, and more specifically with the group of Caroline Corner. And there are 2 groups on Earth being able to grow, I would say, almost single crystals. So it's not really single crystals. So you can see here a specimen, which has been processed by powder bed fusion electron. And you can see that here with this optical observation, you have this central part, which is basically almost single crystalline. And the strategy here is like for Bridgman casting is to establish almost vertical thermal gradient during processing. So very hot process overall. They are obtaining a very, very small dendritic structure with primary dendrit arm spacing of typically 10 to 20 microns. So meaning that you can then do solution treatment at lower temperature or shorter durations. And they have been able to obtain a microstructure very, very similar to a conventionally processed single crystal. And from the work they are doing in Germany, within the very large program called the Transregio SFB 103 from atom to turbine blade, they have been characterizing, in collaboration with the University of Bochum, creep properties and also low cycle fatigue properties. So here you can see that creep properties are very similar to conventionally processed material as soon as solution heat treatment has been performed, so not really surprising. So you can see here creep properties at 1050 C, 160 MPa, and 850 C, 600 MPa. And here you can see some low cycle fatigue properties at 950 C, 0.25 Hertz, but at a very, very high stress ratio, meaning that overall those low cycle fatigue properties are mainly controlled by creep damage. So it's not really a true fatigue test. So what we did, we decided to work together and to do a true fatigue test, and especially to do VHF, very high cycle fatigue tests. So this kind of test, there are very few teams able to do this kind of test on Earth, only 3 teams. So one at UCSB and University of Michigan within the groups of Professor Pollock and Professor Wayne Jones. Here at P prime, and another group in China at Beijing Institute of Technology, working closely with Leicester University. So basically, the principle is to design a specimen so as to reach the frequency of resonance of this specimen at 20 kilohertz. And those conditions are really important from a certification point of view, because airworthiness authorities are imposing criteria with respect to high cycle fatigue, very high cycle fatigue failure at such frequencies, because a blade can vibrate in bending mode during service, and we need to take into consideration possible failure due to this. So the machine we have, and we have a second machine under development here, we are typically using induction heating, temperature measurement with a pyrometer, and we are coping with possible self-heating during the test. So we have been able to establish a very, very large database, probably the largest on Earth for this class of material at 1000 C. And that's not all the data points we have. We are more than 400 data points at this condition, with results you will see up to 410 to the power 10 cycles. And most of the tests have been done by Alice Cervellon and by this lady, Luciana Maria Bortolucci or Mastroni, working on CMS64 processed by additive manufacturing. So I'd like to show you more specifically the results on AM process CMS64. So here we have a database of CMS64 process with a large casting, meaning very large casting pores. Database of CMS64 process with small casting pores. And in all those cases, we have crack initiation at internal pores, the largest ones. Here, you can see AM specimens which failed almost immediately because we had the presence of high-angle grain boundaries. I just want to go back a little bit earlier. If you can see that here in those blanks, we have polycrystalline shells around, and when we do a heat treatment or when we add a heaping stage, we may have a growth of this layer up to areas from which we are removing our VHF specimens. And from this, we can see, and we can say that the VHF test is really a killer test because we have almost immediate failure. Also, during those tests, something you can observe from this SN diagram is that we have not been able to achieve very high alternating stress simply because we have been facing self-heating. And the reason behind that is that the material is full of dislocation inherited from the process, and we have difficulties to get rid of those dislocations. So that's something also we have to work on, and probably using another mode of VHF testing using a pulse mode for that. But from the successful test, you can see that the AM material performs very well, well in excess of, let's say, our reference materials with small pores. And we have been able to observe crack initiation from an internal site, which should be, and we are not 100% sure about that, which should be a low-angle grain boundary because it was a heaped specimen. And all the other specimens fade from the surface through an oxidation process. So that's the longest ever test we did, which lasted more than 500 hours. And when we are able to get rid of pores, then we have crack initiation from the surface controlled by oxidation. So it means that it's in those conditions at high temperature, probably we have no fatigue limit. If we would decrease the alternating stress, we would have a decrease, progressive decrease of the applied stress. So I don't want to enter into too much detail on the failure process because I think I will be lacking of time. But with those experiments, we have been able to identify an environmental limit for this class of material, and probably there is no fatigue limit for this class of material, whether they are processed by conventional processing, so Bridgman casting or liquid metal cooling processes, followed by heap, or processed by additive manufacturing. Okay, so now I want to finish regarding the question of is it the additive manufacturing as a repair technique? That's where is the market. Personally, I really trust the fact that this is where we should introduce additive manufacturing for aero engines applications and for repair purposes. So we have a large program running here at P Prime with the collaboration of Safran Aircraft Engines, the Safran aircraft plant at Châtellerault, 15 kilometers away from here, which is the repair center for both GE and Safran engines, so for CFM International. So we have 2 PhD students working within the context of a program with financial support from Europe and the Nouvelle-Aquitaine local region. So Marjolaine Sazra and Romain Bordas. And we have a large team involving colleagues from Safran, and here at P-Prime, and especially Asdin Italy, who is doing incredible job in terms of analysis of porosity and developing models. So basically, we are working with walls, which are built by laser metal deposition powders. And we are working with WASP alloy and 718. Today, I will only show results on WASP alloy, which is a gamma prime strengthened alloy with nearly 25% gamma prime. We have been able to do the EBSD maps, so very typical microstructures for this kind of process. And the first thing we are studying is the role of heat treatment. Since we are repairing components, is what kind of heat treatment we can apply without degrading the properties of the substrate we want to repair, but improving the properties. And that's a tricky issue. I just want to show you here the case of CMT processed WASP alloy. So that's a kind of wire arc additive manufacturing technique. So here you have the tensile properties at room temperature of CMT processed WASP alloy, vertical direction, so as built vertical horizontal, and in which we introduce a subsequent heat treatment. And what we learned from that process is that just after the CMT process, we are out of equilibrium. And that's something important when you think about the relaxation of residual stresses, because on the one hand, you introduce residual stresses due to the thermal field and the buildup of the dislocation density within the material during processing. But on the other hand, you need to think about improving monotonic properties without degrading the substrate, which is a tricky issue. And we have experiment which will start next week on this with Sandra on the Salsa line to understand how we can develop heat treatments to both relax stresses and trigger the precipitation to optimize subsequent in-service properties. So we did several characterizations at different scales. We looked at the precipitation. You can see here that's a very, very fine precipitation in as-built plus relaxation heat treatment. The precipitates are the very, very small black dots here. So that's 100 times magnification. So precipitates are something like 5 to 20 nanometers. And we have several pores for LMD powder processed materials, depending on the processing. What we are doing is that we are characterizing all the specimens by tomography, X-ray tomography, to be able to correlate to the subsequent properties, tensile, fatigue, and creep ones. I just want to show you some creep properties at very high temperature, 850 C, 160 MPa. For vertical direction, horizontal direction, weak anisotropy in terms of primary, secondary creep stage, and we just have an earlier onset of tertiary creep in the vertical directions, which is mainly coming from the spatial distribution of the pores, which can trigger earlier onset of nucleation of cracks at specific grain boundaries in specific sections. And this is something we are understanding from the pore size distribution and spatial distribution within the build. Something I'd like to tell you here also. So we have plenty of results. I'm just showing 2 typical results. We also did vacuum tests whose creep life in this condition is in excess of 800 hours. So that's something we are also trying to understand. And finally, the key challenges for us are the following ones. So here is the typical component we want to repair. I cannot give the exact dimensions for you because that's something confidential, but that's a part having a diameter of nearly 1 meter. And we are repairing the sealing parts here. And the size of the sealing parts are typically a couple of millimeters in thickness. couple of millimeters in ACE. It means that here you have tomography reconstruction of this kind of repaired part. And we have a given distribution of pores, which is typically different from the one we have in the walls. And our strategy is to build walls with different processing parameters, meaning different pores, different distribution of pores, so as to reach and to try to probe the mechanical properties of those very, very small parts from which we are not able to extract specimens to do conventional creep and fatigue tests. So that's a very specific topic from which we need modeling tools so as to approach the properties of those parts which are typically submitted in service to creep deformation and fatigue fretting issues. And with this, I'd like to conclude my talk just on time on saying that for this class of material, high-strength nickel-based superalloys, the fatigue properties and to a lower extent creep properties are mainly controlled by defects inherited from the AM process, so typically pores, lack of fusions. Once these defects are removed or limited through heaping, for example, then the anisotropy and the environmental degradation may contribute to creep and fatigue properties. And I don't want to read everything here. We need really modeling strategies, to develop modeling strategies to probe the actual service mechanical properties. And with this, I'd like to thank all those colleagues, collaborators, companies with whom this work could not have been possible. Thank you.
Thank you very much for this nice presentation, which highlights the interest of additive manufactured nickel superalloy for aeronautic application. So thank you again. Quick question from the Q&A chat, please. Do you think there is a potential to improve performance through the use of pinning?
Yes. So in fact, we can use pinning for fatigue. My feeling is that it's more interesting to use in situ pinning. There are some processes developed, typically wire deposition, then pinning, then wire, then pinning to allow in situ recrystallization. So I feel that's a very nice way. It's not suitable to all the AM processes. Subsequent pinning, I feel it can be useful for fatigue properties when you have crack initiation from the surface, but overall, that's another process in competition with heaping. So for this class of high strength material, I would not go to pinning except if really necessary. For other properties, I mean, typically fretting.
Okay, thank you. You talk about a very important general aspect about standard thermal treatments not suited for additive manufacturing consolidated materials. Mm-hmm. Do you have ideas of possible optimization for thermal treatments in superalloys?
Yeah, so unfortunately, initially for this WAM workshop, we should have had a talk from Eric Lass from the US, who is really a specialist about that. Basically, we have to cope with when we are dealing with fusion, or let's say we are speaking about welding type processes. We always need to take into consideration the dendritic segregation, and especially the dendritic size. So that's a diffusion process. So I took the example of CMS64, which is a single crystal process by additive, in which we have very, very small dendritic size. And with this, the colleague from Germany have been able to develop solution treatments, typically 1 order of magnitude shorter than the conventional ones, just because the diffusion lengths are shorter. However, when we deal with repair applications, so I'm speaking strictly on the materials property. Now, if we move to much more structural properties, typically repair purposes, one of the key issues is to be able to relax stresses without affecting the substrate, trying to avoid crack initiation during the relaxation stage, and in the meantime to optimize properties. And I feel that for repair purposes, we have a really empty space, which is highly dependent on the methodology of each superalloy. So, for example, the rules that we will develop for 718 are totally different in comparison to the rules we can develop, or the recipes we can develop for gamma prime strengthened material, in which we have very rapid precipitation of the gamma prime precipitates. So for me, it's difficult to tell you, okay, we have to do this or to do this. We have to consider a specific alloy for this.
Okay. Thank you very much again, Jonathan.
Thanks.
So the next speaker is Mr. Nicolas Lemens from Siemens. So he's a research engineer in digital software unit at Siemens. So his main topic is fatigue behavior of additive manufacturing processes and the development of associated software application for fatigue prediction. So his talk today deals with digital value chain from process to performance prediction in additive manufacturing. Please, Mr. Lemens, the floor is yours.
Thank you very much, and good morning, everyone. Just to check, can you all hear me okay?
Okay, perfect.
Okay, then I will start by sharing my screen. Can you see the presentation?
Perfect.
Okay, so good morning, everyone. My name is Nicholas. As said, I work for Siemens, but if your first instinct when you heard the name Siemens was to think of kitchen appliances, I have to correct you a little bit. I work for a different segment of Siemens called Digital Industry Software. And what we do is we try to provide simulation software, design software, and test software to industry to support them in designing their components and analyzing their components. I'm part of the research team within Digital Industry Software, specifically additive manufacturing research, where we try to develop and absorb methods specifically for additive manufacturing. And the ultimate goal that we have is to develop some set of tools that would allow one of our end users to simulate the performance of his or her component, taking into account the full set of choices you have to make when you want to print something with additive manufacturing, and to be able to do that in a predictive way with the bare minimum amount of testing required. Now, obviously, you would say that that challenge has existed for a long time already, because you also want to be able to do that with conventional manufacturing. So why would this be a separate topic for additive manufacturing? And to answer that question, actually, we have to look at the promise of additive manufacturing. Let me just see if I can minimize some of these things. So the promise of additive manufacturing, and that's where the main issue starts, is that you get this new range of freedom in designing, and actually optimal design, it's just a push of a button. The component you see in the picture here is an example of a bracket for an automotive application, and it has been topology optimized. You get this organic shape that with almost no conventional methods can be manufactured. So without the existence of additive manufacturing, this would not be possible. But because we are able to print this geometry, we can save up to 50% of the weight of this part. So it's an important step forward in optimizing material usage and just perfect design. And on top of that, additive manufacturing also offers us the ability to customize each single print we do. So complexity is free, and especially in medical applications, that's a very relevant feature to have. Now, in itself, that's all very nice, but then if we look at what the cost is of this extra freedom that we get, that introduces us to the problem of performance prediction of additive manufacturing. Because actually what's happening is that all this increased flexibility we have, all this process control that we get, it leads to a significant increase in complexity. If we talk about performance and we focus on fatigue life, for example, then in a normal analysis, you would consider for fatigue life three distinct properties. The first one is the geometry of your component. That's an important one to know. The second one is the material that you're going to use. And then the final one is the loads that are being applied to your component. And if you know these three as individual properties, you can predict a fatigue life. That's the normal way of looking at fatigue for conventional manufacturing. But when you step into the domain of additive manufacturing, you have to start taking into account the manufacturing process itself. And because of that single extra layer that you have to account for, all these parameters or all these domains start to interact with each other. And that means that, for example, the material performance that we have here, it becomes dependent on the manufacturing process itself, but it also becomes dependent on how you orient your component within the build chamber, on the printer settings that you used, and it becomes dependent on the geometry that you have. Because if you have thin-walled features, for example, the local material properties will differ from the bulk material. And that's an important one to know. Also, if you cannot print the precise geometry, or if you have some features that you have to redesign because of the printing process, the load introduction might be different. And so that means that everything starts to interact with everything, and predicting fatigue life becomes very difficult, even more difficult than for conventional manufacturing. So if we ever want to get to this fatigue prediction, which is accurate and reliable for additive manufacturing, then there's no way around it. We have to account for the process first, so for the manufacturing step. And based on that process, we have to predict the properties and the artifacts that you will get. And once you know those, you need a material model that is able to account for the effect of all those properties, and that can finally tell you what performance is of your component. And to give you some examples of these properties, process-dependent properties that we consider now in our research, and to be clear, this is ongoing research. So we don't have the final answer yet. I think everyone in this workshop and in the world is working towards getting solutions for this, but we are not there yet. But one of the properties we consider is surface roughness. Now, surface roughness, it has existed in any kind of manufacturing, but when you go to the level of additive manufacturing, there are some extra complexities, because surface roughness is no longer a property of the component. It becomes a local property, because depending on the orientation of your component, you get different surface roughness. For example, in the picture here, the part that is almost perpendicular to the build direction has different surface roughness than the part here at the bottom. Also, the post-processing that you use will affect the surface roughness. And while in itself it's already difficult to work with, all the surface roughness changes, they act as notches for the fatigue life. So they are important to know so that we can properly compensate for their contribution. And then again, in additive manufacturing, you have this additional complexity that surface roughness you should not consider just as a separate property, but actually it's going to interact with other properties as well. We all know that printing a perfect part in additive manufacturing with 0 defects is almost impossible. So if you have this surface roughness and you have a porosity that is just below the surface, it could actually be that the two are going to start to interact with each other and that they have a combined effect on the fatigue life. So that's also something to consider. And then there's a couple other properties that we are looking into. Of course, there's even more than what's on this slide, but these are the ones I would like to mention. The surface roughness I already mentioned, but other ones, for example, are the residual stress. Here also, they build up during the layered manufacturing process, but if you heat treat it, they can change again. And if you machine it, depending on the type of machining you apply, you can again introduce different residual stresses. That means that certain areas of your component might have a mean stress effect, which affects the fatigue life. So it's important to know these. Another one is microstructure. The previous talk has illustrated quite well how microstructure can affect performance. And here also the additive process gives us an additional challenge because you get a unique microstructure just because of the heating and cooling rates. And depending on the geometry of your component, the microstructure is not uniform throughout the part. If you have thin walled sections or you have bulk parts, or you have parts that are very close to another part in the build and see a lot of heat from that, they can all affect the microstructure. And then the final one I wanted to mention is porosities. And here I want to emphasize the local effect of these all these properties and how important they can be, because porosities, essentially, they are dependent on the local conditions of the melt pool. And those local conditions, they are affected by the hatching strategy and the processing parameters. So if, for example, you have an overhang where the material tends to heat up a bit more, you could see that you get more porosities in that region than you get somewhere else in your component. And then depending on the type of loads you apply to your geometry, those porosities could either be in a very critical region or could be meaningless. So it's important to take into account that all of these properties that I mentioned here and many other of them, they are not a global property of the component, but they are a very local property that fluctuates throughout the entire component. And what we try to do then to be able to predict how all these properties are going to affect fatigue life is to build predictive modeling simulations that allow us to predict some of these features. And for example, we do CFD simulations. That's a picture you see here on the left, where we, for example, could try to predict keyhole porosities during the printing just based on the process settings. Of course, CFD simulations are not cheap to run. They take a very long time. So in an industrial setting, this is still not a perfect solution because it just takes too long if you would want to apply this to a large part. It's actually not even feasible to do that today. So what we do is also look at other methods that are faster, maybe not as accurate, but that strike a good balance between accuracy and performance. And one of those examples you see here at the top is where we try to predict the temperatures that exist during the process, taking into account the laser settings, the scanning strategy. And based on that, we want to predict the temporal evolution of the temperature. And if we have those, we can actually look towards things like grain growth prediction, what you see here at the bottom. And our final goal is to be able to capture everything that happens during the printing process, to know what features you can expect in your component, and then to be able to predict from that the performance of your component. Now, to be able to predict the performance of the component, there is a second challenge. You not only want to know all the properties or all these artifacts, but you also have to be able to know how these will work together to get to a certain fatigue life. And if you look at the top picture here, this is a literature study that has been done on Ti-64, added and manufactured Ti-64. And what you can see there is that depending on the precise type of processing that was done on the coupons, you get a fatigue life that has a huge variation. So this means that if you want to accurately predict lifetime of your component, you actually have to know pretty accurately all the process parameters or the precise condition of your component, because if you don't, you have no way of picking the right SN curve from this scatter plot. And what we know is that in order to be able to predict fatigue life, actually we start from the AM properties. So things like printing direction, post-treatment, energy, velocity, and all those properties, they affect the local properties. So not the global properties, but actually very local properties like surface roughness, residual stress, and microstructure. And all those local properties then finally come together into the final component fatigue life. So predicting component fatigue means taking into account a lot of influencing factors. And that means that we need to build a model that can account for all those factors. And the question then is, how can we build a reasonable simulation framework that does a good job in predicting component behavior without requiring a huge amount of test data? Because fatigue testing is expensive. And if you just look at all the degrees of freedom, if you would do a brute force approach, it would be impossible to test all these possible combinations. So the idea we developed and we are developing is an AM-aware durability simulation. And the concept that we use here is that actually on the right side, you start from your CAD model. And because we are 3D printing, it's more than likely that this CAD model is available. So that's already good. And with that CAD model and knowing how we want to print, we can go towards automated feature extraction. So that's what you see here. It's a simple example that we did where we predict surface roughness based on the orientation of the component within the build chamber. So those two we feed to the durability solver in order to know the geometry, the loads, and also all these features that I discussed. And then on the other side of the diagram, we have to build a fatigue model. And to build that fatigue model, we actually start from a limited set of material data. And then we have to convert that into a physically meaningful material model that can also interpolate or extrapolate beyond the test data that we have. For that, we use the machine learning application. And to show you a bit more information, our current implementation is actually based on a Gaussian process. The reason that we chose that is that, first of all, a Gaussian process, it's a statistical estimate. So it's the most likely estimate of your fatigue life. So it's not going to give you a single fatigue value for a certain input condition, but it's going to give you the expected fatigue life and the standard deviation that comes along with it. And that's an important thing to know, because we have a multi-dimensional input parameter space, and it's very easy to try and predict component performance that is far outside the training data that you have available. And if you have no estimate of the standard deviation of your prediction, then you have no way of knowing how reliable your prediction is. So that was an important feature to have. And the second one that was very important is that most machine learning and artificial intelligence tools, they have been conceived with the spirit of big data analysis. Now here with SN curves, we are actually confronted with the opposite. We have very scarce data sets, and it's unlikely that we will ever have a broader data set than just very scarce data. So Gaussian process still works pretty well with those limited data sets. And then the last thing that was very important to us was that we wanted to have methodology that still works if you change material, that still works if you add extra input dimensions, and that makes minimum assumptions about these relations between inputs and outputs. Because for some materials, you might see strong correlations between two factors, and for some other materials, those correlations completely disappear. If the model a priori assumes interactions between these parameters, then it's not going to be universally applicable. So that was important for us to have. And to just illustrate briefly the results that we've achieved so far, I wanted to show you some results that we did on a steel turbine blade analysis. So it was a 316L stainless steel that was used. And to build our fatigue material model, we started with simple coupon test data. So we did high cycle fatigue test data. All of them, of course, were printed in 316L, but they were printed with a fixed set of processing parameters. The only things that we changed were print orientation, the surface condition, and the heat treatment that was applied. So that gave us a small set of test data that we could use to train our machine learning model. And the input parameters that we considered in this study was just surface condition. So we looked at the roughness of each sample, the print orientation, because we wanted to account for orthotropy in the material, and the heat treatment that was applied to the samples. The pictures you see on the left are two actual results from our machine learning using a leave one out principle. And what that means is that from all the SN curves that you have from testing, you take one out of the training data. You train your model with remaining set, and then you predict that one SN curve that you removed from the training data, and you compare it to the actual measurements. And that's what you see for two different conditions here in the pictures. The red line is actually the mean prediction. The light red shaded area is the standard deviation. And then the black marks are actually the test points. So you see that our model fits pretty well for both of these conditions. And we had a total of 9 different conditions. I could show 9 plots here, but it would not be interesting for you to look at, but they all have similar performance as this. So we were pretty pleased with that performance, given the fact that it's actually a very small data set, and it still was able to properly predict the outcome. So then we looked at the component itself. You see it on this picture here. And this component was tested experimentally in a shaker setup. So this is the part of the shaker. And there's also a strain gauge applied here to the blade itself to be able to know how much strain and stress is actually applied during the test. We replicated that with an FE model. So we did model analysis where we tuned the load so that we would get the same strains as the strain gauge measured on the component. And then we did a predictive analysis where we looked at principal stresses, the roughness, and also the orientation of each individual element relative to the build chamber orientation. And then if we look at the first results we got, if we just look at the durability results and the stress results, we see that failure is actually predicted at exactly the location where we saw it in each of the experiments that we did. But more importantly, if we look towards the actual numerical predictions, we see that we get still very good results. So on this plot here, you see the dotted line, which is the prediction that we did with our AM-aware durability solver for the component. And then the crosses that you see, they are actually the results from the experimental tests. So you see that our prediction always, or all the test points are within the 95% confidence interval of our prediction, which is a very nice result, especially taking into consideration that if you look at this picture, you see that we have very strong stress concentration. And normally you have to account for that. You have to compensate for the notch effect. And we did not implement this yet in this study. So we are confident that if we would implement this notch compensation, that our prediction would match even better with our experiments. So that's a very promising result, but of course, it doesn't mean that we are there yet. What we have seen so far is that we get very promising results in several of the individual domains. For example, surface roughness prediction, porosity prediction, fatigue life prediction, but integrating and interfacing all of these individual domains together is still a work in progress. On top of that, we want to further enhance the property prediction capabilities. So we want to be able to predict even more properties. And we also want to reduce the dependency on experimental testing. As I said, we want to ideally come to a point where we only do the bare minimum of testing and all the rest comes from simulation. And for that, for example, we are looking into a simulation framework to predict the influence of surface roughness. And then finally, we want to integrate this entire workflow into a seamless experience for the end user, so that he can just, at the click of a button, predict the entire performance of his component very easily. So what we want to achieve then, first of all, we want to be able to predict these three different domains: the manufacturing process itself, the resulting material properties, and the individual properties such as porosities and microstructure. And then based on those properties, we want to predict part scale performance. Once we are able to predict that, we actually want to reverse the problem. We want to optimize the manufacturing process based on what performance we need to achieve. And ultimately, once we are there, this will enable us to tailor the printing process to achieve exactly what we need. And that will still, again, allow more optimal material usage, faster printing, and it will just reduce the cost of additive manufacturing. So that's the ultimate goal that we have here. And with that, I want to finish my talk by acknowledging two funding agencies that helped us in doing the work that you've seen here. I also want to thank two of our colleagues at Siemens Corporate Technology, who worked with us on a different projects to be able to get to this point. So with this, I finish my talk, and I'm open to any questions you might have, either during this conference or via email. You can also still reach me if you have questions. Thank you.
Thank you very much for your presentation, which show to all of us the complexity of fatigue mechanism in LPBF process and components, and also the necessity of multi-scale modelization. So we are a little bit late, so perhaps just a quick question for Mr. Alvarez. about the minimal number of tests needed to feed your machine learning algorithm for fatigue prediction?
Mm-hmm. At this point, yeah, it's a bit dependent on what parameters you choose to vary in your experiments, of course. If you never think about changing the temperature conditions of your component, there's no need to study that input parameters. So that's one of the driving factors. Where we achieved good results now was with 9 SN curves. So that's where we got good performance, but that was only considering these 3 input dimensions that I mentioned. So it's a bit dependent on how many different parameters you want to take into account. We never actually try to find the absolute minimum right now. Our idea is more to be able to replace SN curves with simulated SN curves so that we can further reduce the amount of experiments needed.
Okay, thank you very much for your quick answer. Now we can switch to the next presentation by Mr. Manuel Sanchez Ponchela from ArcelorMittal. So he's a member of the additive manufacturing department. So his researches are actually focused on mechanical behavior from microscopic to microscopic scales during 3D printing and post-treatment stages. So his talk today is focused on residual stresses of steels during LPBF process. Please, you have the floor. We can't hear you, Manuel.
Okay, now?
Yeah, perfect.
Okay, thank you, sorry. Yeah, so let me share my screen. Okay, can you see it?
Yeah, not again.
Yes, can you confirm me if you can see my screen?
No.
No, not possible. So why not?
Yes, okay.
Okay, yes. Let's remove this. You can see it now.
Yeah, perfect.
Okay, sorry for the inconvenience. Well, first, thank you very much for inviting us to this workshop. We are very happy to be here and share with you some insights of residual stresses in steel in laser powder bed fusion or SLM, their distribution, mitigation, and simulation. So let me first introduce ArcelorMittal for those who might don't know who ArcelorMittal is. So ArcelorMittal is one of the world leaders in steel making and mining companies in the world. We are present in many countries, and yeah, ArcelorMittal is one of the largest producer of steel in Europe, America, and Africa. Also, we have a big global R&D network located in 11 different places, most of them here in Europe, but also we have some in America, like the ones in Canada, East Chicago, and Brazil. So we are in the north of Spain. In the north of Spain, we have three centers, two in Asturias and one in the Basque Country. I belong to one of the centers in Asturias, which is one called New Frontier. And here we studied or researched hot topics like big data, machine learning, and data mining. This is the digital factory, new materials and nanomaterials. 3D printing, which is the department my colleague Juan Manuel and me belongs to. Sustainable resources for focus on ArcelorMittal mines, And since the COVID-19 outbreak, we started to develop a new lab called BioLab for activities to fight against the COVID. So now entering in the residual stresses and residual stresses in additive manufacturing. So usually people has a bad image of residual stresses because they can lead catastrophic failures, especially when they are not accounted, and it's right. But also it's true to mention that sometimes residual stresses can be beneficial and they are induced intentionally for instance, for improve fatigue performance, like shot pinning or some examples that has been put on the table in previous talks from today. And why they are important to measure in additive manufacturing? Because additive manufacturing is a very growing industry with a unique thermal history, very high cooling rates with successive micro size melt pools, where different printing parameters are possible, and you cannot even like tune them on the spot. And also you can use different printing strategies, which can lead at the end of the day different microstructures of sister samples or even samples from the same batch. So it is important to know the stresses and their distribution on the samples as built in a heat treatment if you do it for stress relief, and also when you remove the sample from the build plate to reduce possible distortion of the geometry, and also to assure the structural integrity of the component. So here I present our case of study. We have been working with ELN in a very fruitful collaboration. We like it, this geometry that we proposed, because it's a simplified geometry, but already representative of many final compounds like nozzles, pipe, valves, pressure systems, and so on. So we study the cross section of the sample here between the both cylinders, because also this geometry combines a joint region with a hollow part, which is also one of the main advantages of additive manufacturing, to reduce the number of processing steps. So you build this sample at once, and you don't have to drill it or then weld it and so on. We select stainless steel 316L because it's a very well-known steel in additive manufacturing, very relevant for industry, and also it's very easy steel to work with in additive, with a very stable phase, so it's easy to work with. And samples were measured still attached to the build plate, because we wanted to guarantee the stress state that is produced during the process. So if we remove the sample from the build plate, we would be releasing by distortion these stresses, and we wanted to measure the real residual stresses that came from the process. And we have two initial goals. We were working with ELN. First was to study the ability of stress relief by a heat treatment without changing or not changing much the microstructure, because we want to guarantee the mechanical properties of the part, and validate two modeling approaches we use for predict residual stresses with different degree of simplification both. So we did a metallurgical analysis of the component, both components, the sample as built and the sample heat treated, We already have developed previously the printing parameters for this steel, so we could assure a full dense part without macroscopic defects. So there's no porosity or cracks inside. And looking closely to the microstructure by SEM images, we saw a very fine microstructure with fine cellular solidification cells with average diameter below the micron, so very fine. And also this microstructure was preserved after the heat treatment, which is good, is what we pretended. We measured this cross section by lab XRD, and both samples, and also powder from the same printing batch, and we saw that this mainly austenitic phase for this steel, which is not neither surprising, as this steel is very well known to be very mainly austenitic. So this is also important inputs for measuring the residual stresses to know initially the microstructure that we have. Also, we performed some EBSD maps because we wanted to measure the crystallographic texture of the part, but also the grain size and the morphology of the grains. So we can see that we have a very heterogeneous distribution of grains with some elongated grains surrounded by much finer grains between them. And yeah, as I said, a heterogeneous distribution that it's also mainly preserved after the heat treatment. In average, we have between 60 and 70 microns grain size in average of all the grains, so very fine microstructure. Then crystallographic texture, we found that there are some planes that are preferentially oriented, 15 degrees tilted from the building direction, which is also typically in additive manufacturing. There are many literature showing exactly these results. But if we check the scale, we can see that texture is neither strong. And also the 311 plane, which is the one used for measuring residual stresses and strains in FCC systems like austenite, has no texture at all. So here is when we brought the samples to SALSA. We measure the three main components of the components, align it with the scattering vector. So the axial component here, radial component, and we measure as well the tangential. And then here, those are the happy faces after successful measurements and results. So here I compare the results obtained by the axial strain at the sample as built and after the heat treatment. So it can be seen that globally there was a strain relaxation after the heat treatment, which is what we were looking for. And also what is very interesting for us is like the sharp gradients that you can find in the Z direction. For example, if we look to this L2 line with which is representative from the inner cylinder surface, there are very sharp gradients in a small portion of distance, but also there are gradients between the inner and outer surface, so in the XY plane. That's something that we were not really expecting. And now I present you here an overview of both models that we used for predicting the residual stresses. So first one is model based on the inherent strain method, which is a purely mechanical model. Here in this model, we input the elastic strains and answer of the material, and we calibrate the inherent stresses experimentally by cantilevers, and with all that, the model calculates the inherent strain, and the idea is that they simplify all these strains to a unique inherent strain per layer. As it was previously said, at the end of the day, these models, they have a degree of simplification, because to perform high fidelity simulations of already this kind of samples will last for really a lot of days and with high computational cost, and it's not affordable. So in this case, there is a macro layer activation. Initially, all layers are deactivated, and then there are a successive macro layer activation from the bottom to the top, and the final part is reached. And the stresses are calculated by finite element at each node of the mesh. This is this first model, and then the second model is a thermomechanical model, which is a little bit more sophisticated. It counts for it calculates initially the temperature field, and after calculating the temperature field of the macro layer, it runs the mechanical calculations. So in this case, what we have to feed to the software the elastic and plastic behavior of the material at different temperatures. That we do that by experimental tensile curves. And in this case, we don't need to calibrate the inherent stresses. They are calculated in the software by input the printing parameters and the scan strategy. Even though scan strategy, well, it is used because they use it for calculate how much time it takes to print each layer, and also because there is it has this model, a pseudo high fidelity micro model, where it solves with few laser tracks the thermal behavior that then extrapolates to the macro layer. But it's not it doesn't use the scan strategy, let's say, for performing high fidelity simulations. And then, even though this model does not need calibrations, SimuFact recommends two types of calibration. One is experimental calibration with also a similar cantilever geometry that is used for calibrate the thermal expansion coefficient and then calculate the stresses due to the thermal stresses. And another is a pure numerical calibration, where we divide the laser energy input from the machine for the fraction of the laser that is used for melting and bonding the powder with the part, and then the fraction of the laser powder or laser energy that is dissipated by the surroundings and the previous layers. So here I compare the stresses predicted by both models with the von Mises stresses measured by neutron diffraction. It's easy to see that there is a big discrepancy between the prediction of both models and the real stress is measured experimentally at SALSA. And this is mainly because of the degree of simplification, and they do macro layer activations. So it's very difficult for the model to really predict a stress gradient inside the same printing layer. So in the same XY plane, usually those models give us a very homogeneous stresses, while it's not the case. Also, in an exercise with ELL, we are already working on how we can improve the experimental results to be more useful for simulations. So we are in this study, we were assuming that the three main directions that we were measuring are aligned with the strain tensor at each point. That might not be also the case. So we wanted to reconstruct the full strain tensor to better calculate the bone misses stresses at each point, and also because this to capture anisotropy in the part that will be very interesting and for simulations as well. So I conclude the talk, summarizing and doing a wrap up of everything we were explaining. So first, we propose a heat treatment for 316L in SLM that is good for reducing the residual stresses without modifying much the microstructure. That is what we wanted. In this line, we are now running some tensile tests performed the specimens after this heat treatment to assess the mechanical behavior as built with the one after the heat treatment. We compare the experimental results with two modeling approaches that none of them predict accuracy these stresses, and this is because first, the degree of simplification, the voxel size of the mesh that is much bigger than the melt pool, and also because at the end of the day, these both models, the main purpose is to predict the macroscopic distortion of the part, and they do it right. But what they do not do right now is to predict the residual stresses. So to better capture this stresses distribution, it is needed to implement the scan strategy. This is key, and also to have better crystal plasticity implementation of the material, to account for the intrinsic heat treatment of the material from a layer from the upper layers when they are printed. So yeah, this is everything. I can conclude my talk here, and I will be very happy to answer any question if there is, and also today also by email or something. Thank you very much.
Thank you very much, Manuel, for this very interesting presentation. I have a question on the chat for you. Mm-hmm. How do you incorporate the scanning strategy for the thermomechanical model? And is flash heating used to impose the energy on the new elements, or is it another technique to be used?
Yeah, so it's what I pretend to say, that in reality the scanning strategy is not account for solving the residual stresses. It is not used in the mechanical simulation. It is incorporated, but it's a micro high fidelity model that only there are few paths that are done to solve the thermal behavior of each of this layer that then extrapolates to a macro layer. So this is what how it is called, this one. But those are commercial softwares, and we don't have access to these details on how they do this micro high fidelity simulation for I insist the thermal behavior. Then for the mechanical behavior, they don't use it.
Okay, thank you. I have a question for you, Manuel, on the microstructure aspects of your thermal treatment. We know that in additive manufacturing microstructure, you have a strong effect of dislocations. I think that at 700 degrees, you have a strong annihilation in your case on stainless steel.
Excuse me?
During your thermal treatment at 700 degrees, do you have dislocation annihilation?
Well, we didn't went to TEM really to after the heat treatment. So maybe this is something that could be interesting for future. We have done some TEM analysis on the sample as built, and indeed there are lots of dislocations and micro segregation in between the cellular cells, but we didn't go so deep in the heat treatment and after the heat treatment. So first was to have a macro view of residual stress mitigation, and now we wanted to check the mechanical behavior, but macro scale with tensile test. However, it may be very interesting to study it. So probably for a future WAM, we can bring those results, or even in a future publication.
Okay, thank you very much again, Manuel, for the talk. I think now it's time for the break.
Thank you very much. You're welcome.
We come back together in 30 minutes.
Yes, we would like to underline that the chat will be open to everyone, to all participants. So should you have any further questions or thoughts, please share directly on the chat, and we'll stay around to answer your question or to address them to speakers. See you in 30 minutes.
See you.
Il passe.
So I think now it's time to come back to our presentations. So the next speaker is Mr. Jonas Martinez from French National Institute for Research in Computer Science. Jonas is a junior researcher on computational geometry, computer graphics, and generative geometry for additive manufacturing. So his talk deals with the possibility to control elasticity on small-scale geometry with additive manufacturing. Please, you have the floor.
All right, thanks for the introduction. Can you hear me?
Yeah, perfect.
Okay, just to check. So I would like to first thank the organizers for giving me the opportunity to talk in this workshop. I come a little bit as an outsider. I have seen some of the previous talks. So my background is not, I'm not in mechanical engineering or material science, but it's more focused on computer science. So basically what we do is we research algorithms. And there is a team that is called MFX team inside INRIA. It's a newly created team. And our focus of interest is basically the application of algorithms to problems arising in additive manufacturing. So we have several lines of research. One of these is focused on how to devise efficient algorithms that generate small-scale structures. And the problem here is basically, as we will see, that you have an enormous amount of geometric complexity, and you need to devise efficient algorithms to do so. And we will start by the focus on our work, which is mechanical metamaterials. There is actually no consensus on what is a metamaterial on the community. So here I'm going to stick to one definition, which is that a mechanical metamaterial is basically an artificial structure that has some mechanical properties that are defined by their internal structure. So you have some here some interesting examples that are very well known, such as offsetting metamaterials that have a negative Poisson's ratio. Basically, when you expand, when you do tensile, exert a tensile force, they expand instead of contract, which is something not commonly found in materials. There is also a line of research which we have been very interested recently, which is functionally graded metamaterials. Basically, the ability to spatially control the variations of the geometry, and by doing so, also to control the variations of the mechanical behavior. Another field that has recently got a lot of attention is in topology optimization. Basically, the problem in topology optimization is that you have a set of boundary conditions, some domain. You're given a budget of material to use, and usually you want to obtain, for instance, the stiffest structure. Since we can't control the lowest scale microstructure geometry, this allows for designs that are more efficient. So here you have a real example of a 3D printed bridge. And as you can see, if you focus on to a small window, there is a microstructure there that has been specifically tailored for this domain. Another line of research that also has this bias a lot of attention is how to do at the small scale materials that are at the same time light and very stiff. Finally, there are several applications. I'm just mentioning some of them to give a global view. So we have been also interested in soft robotics with colleagues in Lille, and this is actually a paper of us. Here, the interest is basically that you can get more interesting behaviors of your robot, of your soft robot device, by controlling a metamaterial stiffness. So here you have this kind of rotation device, and on the left you have the behavior you get with an isotopic material, and onto the right you get what you get with a specifically tailored metamaterial. So you can expand the range of possible physical behaviors of soft robotics. And another one that can be interesting, for instance, this paper where you change the internal structure of an arrangement of tiles in order to get some specific property arise. In this case, a happy face. So I will give an overview of additive manufacturing, but I think here the audience is pretty well versed on that. So we consider in our department 3 different technologies. The first is the most widespread and inexpensive fused filament fabrication, where you deposit layer by layer usually. We also consider stereolithography apparatus, where you basically are photopolymerizing also layer by layer, but instead here you are not sending instructions of a path, but you are sending instructions of an image for each slice. And we also have some selective laser sintering machines. So what I want to bring to discussion is that actually when we're designing the algorithms to generate small scale structures, we have to take into account the fabrication constraints that are imposed by these technologies. So not all range of geometries are fabricable actually. So for instance, to take a simple example with fused filament fabrication, usually you need structures that are self-supporting, or you need the use of supports. So basically the space of geometries that you can achieve is constrained. So our common strategy in the works I'm going to present following is basically to find a subset of geometries that strictly enforce the fabrication constraints, and that at the same time expand an interesting and as possible wide space of elastic behavior. So the most commonly used material to do metamaterials is to consider a periodic arrangement of tiles. This is because we can very efficiently simulate the asymptotic behavior of this kind of tiles. And also it's very compact, the storage. However, as many works recently have noted, and there is some challenges when you want to do spatial gradings of properties. For instance, imagine that you have two different sets of tiles with different geometry and topology. Interpolating between one and the other is actually a non-trivial task. So the common tool used by all these approaches usually is to consider homogenization, more precisely periodic homogenization. So periodic homogenization allows us, given a representative volume element that is periodically repeated, extract what is the homogeneous material behavior, considering that this representative volume element size tends towards 0. So here the assumption is that we have something that it's very, very small. And then we obtain basically the average behavior. Another line of research, which is the one we focus our research, is on stochastic metamaterials or random arrangements of metamaterials. So these are less widespread metamaterials. One of the possible explanations of that is that actually it's a little bit costly to simulate their average behavior, but they have some very interesting properties. And one of the ones we really focus is that they allow us usually to do implicit grading of the spatial geometric properties. So for instance, here you have basically a foam where we are grading very progressively from almost solid to almost void density. So basically, in the reminder, you will see that with these stochastic metamaterials, we can do implicit grading as opposed to periodic materials where do you have to take care of the boundary between the tile geometries. So for stochastic homogenization, in order to compute the average behavior, we use a very simple technique, which is called cutoff techniques, which basically consists on considering a periodic homogenization sample. And then the question, which is non-trivial, is to consider what is the window that will give you a good approximation of the average behavior of your random medium. And we know that for some kind of random materials, this approximation actually converges. And last, some of you may have noted that actually our background is on computational geometry and also in computer graphics. And you may wonder why we did end doing metamaterials. So here's the reason. Back in the 80s, but there were some authors in computer graphics which were interested in devising algorithms to do solid structures in a very efficient way. We call that procedural. In algorithmic terms, this means that you can evaluate for any point in a space if this is empty or void with constant time and constant space complexity. This means basically that we can generate arbitrarily large microstructure geometries. And I want to insight in that, we never generate a mesh. So basically, what we always do is to directly generate the instructions that are sent to the machine. This can be either the G code or an image, but we never pass the step of generating a mesh, which is actually non-trivial. And actually, we incur usually in loss of accuracy when we do a generation of a mesh. So here you have another example of procedural structures. And if you want to play with them, actually, you can go to Shader Toy in internet, and you can see that different examples. And what you can see basically is that these structures are entirely defined by a code. So they are not stored as a mesh, but they come from a procedure. So here, what is the general pipeline, procedural pipeline for additive manufacturing? Usually, we print planar slices. So we have at some point a slice. And then we want to generate the geometry inside this slice. So we have some function that for some coordinate X, Y, and Z tells us if it's solid or solid. And just with that, we are able to generate arbitrarily large microstructures because we only are using this predicate. We are never storing the geometry. So we call this line of research procedural forms. And we have three representative examples to show. The first one is one that is targeted to SLA and SLS. And here, I'm going to put again the video. We had the following fabrication constraints. Basically, you cannot have no local minima when you print, otherwise it will not properly be attached. And you cannot have in this kind of technology enclosed voids because they will trap the resin inside. So we thought that having a structure that have convex cells will be nice because then we can ensure that we have no local minima. And if these are open cells, we have no enclosed voids. So of course, the most trivial option is to just consider the edges of a 3D Voronoi diagram. For the ones that are not familiar with Voronoi diagrams, it's basically, imagine that you have a set of points in space. And then for each point, you consider the set of points that are closest to this rather than to the other. This induces a partition of the space with convex cells, and which you can see on to the right. And if you take the edges of these convex cells, you have the edges. So I'm not going to enter into details, but we devise a very efficient procedural computation approach that it's basically some lines of code and that can be parallelized with the GPU. So it can be done massively parallel. And finally, we also did some numerical homogenization. And we actually found consistent results with the literature. Voronoi diagrams have basically this kind of behavior where the volume, the relative volume, is correlated with the Young modulus following some kind of power law. And also the Poisson's ratio remains fairly stable along with the Poisson's ratio of the solid material. So here you can have a glimpse also of some of the results we did. These were printed with an Autodesk Ember, which unfortunately is not available anymore. So you can see that we were able to print very low scale structures. Here you have another illustration, an articulated finger, where we basically are playing with the density on the articulations. Here we have our cute octopus. This was printed with B9 Creator. Up to the date, we're still torturing this octopus and it's still resisting, so not bad for him. So let's go to the second metamaterial that we devised in a procedural fashion. And this one was not an isotopic material as the Bornoi foams, but was an orthotopic one. So I'm going to assume also that all of you are familiar. Orthotopic elasticity is actually a subset of an isotopic elasticity. And basically, given some orthotopic frame, we have that the elasticity varies independently along some orthogonal axes. So here is what we obtained with our approach. I'm going to enter into details. But basically, we were seeking for some material, such as wood, that have better adaptation to uneven loading scenarios. So algorithmically speaking, we also have a control of the point density procedurally. And what we consider is the k-nearest graph of this set of points. A k-nearest graph is basically, imagine that for each point, you connect it to the k-nearest ones, and you connect them under some specific metric. So not the Euclidean one, but a stretched metric, basically. Is the Euclidean one plus some affine deformation. And we can control the angle of this metric and also the stretching factor. And finally, we have another parameter, which is the beam thickness. So this leads us to a structure that has an orthotopic behavior. And more interestingly, the orthotopic axis is aligned with the metric angle. So this is what we verified here. As you can see, we have different angles. And I'm not going to enter into details of this plot, but basically showing you that the orthotopy is aligned with the direction of the stretch of the metric. Regarding the material space in 2D, one note, all these results are considering simple linear elasticity. So we just do periodic homogenization with linear elasticity. So here you can see the space we cover of Young moduli in the X and Y. So it's a pretty wide space, and you can see some samples of this space. This is in 2D. And here the same when you lift up to 3D. So basically you have a free set of points, and you have some 3D metric, and we also cover a wide space. We also did some tests with help of people at Institut Jean Lamour, which is an institute of material science in Nancy, to verify the correlation. And we also got some close agreement between experimental and simulation. And we also did some 3D tests. So as you can see here, on to the right, you can see that you have a structure that basically is tending to have more struts aligned to the vertical direction. And of course, this implies a higher Young moduli in this direction. So here are some illustrative examples. One was purely a design. So this was our initial installation, a design of Lilian Bandal, where he tried to do this kind of chair. We were able to do that also with our k-nearest foam. Here you have also some examples of cylinders with different parameters of the foam. And here another representative examples. So for instance, here you have a gear where the metric is aligning towards the boundary. So supposedly this could help to resist the pressure. This is illustrative. It doesn't come from optimization. It's just to illustrate. And finally, I'm going to show the last work. This one was basically a work focused on fused filament fabrication. So as I said, fused filament fabrication is a very inexpensive and popular fabrication technique, and has a wide spectrum of materials, so it's interesting. However, it has very strict constraints when you look at it from a geometric point of view. First, you cannot have a local minima, because of course, due to gravity, it will fall when you're printing layer by layer. And then there is a second constraint, which is usually called the overhang constraint, which tells you that when you're depositing one layer over the other, you cannot pass some limit of angle. So usually, typically it's 45 degrees, but it can be others depending on the material. So there have been different works on doing metamaterials, internal structures for fabrication. They can be usually broadly categorized as closed cell or open cell, depending on the kind of cell. So we could focus mostly on closed cell because the deposition trajectories are continuous when you look at the slice. And the open cell, it's much more challenging because you have to travel the nozzle from one point to another, and this leaves spurious plastic things. So the first thing we thought was, okay, let's take the Voronoi diagram and apply it for fuselage line fabrication. So here you have a 2D example. Again, this is a set of points that is close to P, and it uses a partition of the space. However, if you look at some edges of this diagram, you will see that some of them actually violate the angle constraint. That is, with respect to the printing direction, the relative angle is greater than 45. Some previous work has used Voronoi diagrams, but actually they have needed to use soluble supers in the interior. And we are completely discard that because we wanted to scale, and this is quite tedious to remove. So here's our intuition. We wonder, can we do something with the metric in order to ensure fabricability? So of course, with the Euclidean metric, it's not possible because actually the Voronoi faces or edges in 2D can have any arbitrary orientation. But if you change your metric to a polygonal metric, such as a square, here you can see something interesting happening. Basically, the edges of your Voronoi cells have a finite amount of orientations. Here, as you can see, it's either horizontal, vertical, or up to some rotation of 45 degrees. So our intuition was that there must exist some distance such that we can have a finite amount of orientations and we can have no local minimum and angle constraint. And trying just this kind of triangle distance proved to be successfully in 2D. So we wanted to extend that to 3D. So let me explain a little bit what does it mean to measure a distance with a polygonal distance. So imagine that you have a convex polygon P contained in the interior of P, and you want to measure basically what is the distance between P and Q. So the distance is basically, intuitively speaking, the scaling factor that you have to apply to P in order to touch Q. So this is this more compact formula below. So this is basically a measure. It's a measure between 2 points. So now we focus our interest on what happens with the set of points that are equidistant between 2 points under some distance. So for the Euclidean metric is basically you put a line between P and Q and you get the perpendicular bisector in the middle. This is very easy. But with this kind of distances, you get more strange bisectors. But we know from theory that they are linear. They are composed of linear patches. And more importantly, they are homeomorphic to a plane. This means that we don't have isolated pieces of the bisector. And that's the key property that we exploit, is that each bisector face is actually defined with the interaction of 2 facets. I'm gonna enter into details of that. So let's go back to the example of the triangle. Let's say we want to verify that our Voronoi diagram is going to verify always the constraints. So what we do is basically we enumerate all the kind of angles that the bisector can have. So with a triangle is basically these 3 in blue. And then we also need to enumerate all the kind of bisector vertex configurations. So actually there are only 3. So as you can see, this is a combinatorial problem. And we have some lemma that tells us that if all the bisectors verify these constraints, then the Voronoi diagram also verify these constraints. So we can prove that the Voronoi diagram is self-supported. So in 3D, what we did is basically to extend the idea and consider a cone that has some base. The apex is following the printing direction Z, And then, as usual, we get some parameters. The first is that this base is a regular polygon. So one parameter is the number of edges of this regular polygon. Then we have another parameter that controls the angle between the origin in the center and the base. Another parameter mu that considers the ratio between the origin and the lateral side. And then finally, we have linear scaling that we apply in the x direction. So I'm going to put all these parameters in a visual action. And of course, a rotation. This is important. We can also rotate this cone. So let's have a look. Here you have a cone below with the parameter theta 25 degrees, and you have the resulting stochastic microstructure. So as you can see here, you have something that it's flattened, but your Voronoi diagram is always self-supporter up to this overhang angle. As you increase theta, for instance, to 45 degrees, you will see that this flattening elongates and you get things more elongated into the printing direction. Then you have the parameter mu. This is a very interesting one. This one, I'm going to show it visually, intuitively. What it does, it controls the amount of vertical walls versus non-vertical walls. All right, so as you can see onto the left, you have almost no vertical walls, but onto the right, you have this kind of more elongated vertical walls. You also have the parameter sigma. This is the stretching. So you see, we start stretching this distance, and this stretching of the distance also incurs into a stretching of your metamaterial. So as you can foresee, mechanically, this means that we will have more stiffness in the direction where we stretch, and in the perpendicular one, it's going to be less stiff. So what can we do? Always keeping in mind that we can do these gradations implicitly just by changing the parameters, as opposed to periodic tilings. We can change the side density of the points that generate the Voronoi diagram. We can also, for instance, here vary smoothly the point, the density of, the parameter mu that controls from non-vertical to almost vertical. And here we can do even more interesting things. So here we have a concentric field of direction, and we can guide the distance with this field. So you can see that you can have materials that are concentric or orthogonal to the concentric field. You can provide any arbitrary as long as it's defined per the slice. So regarding the algorithm, it's procedural. So at some point we have the current intersection. We need to send the G code to the printer. So we have a procedural algorithm that is very efficient to label what points belong to each cell. Then we extract the boundary, the interface between the cells, and finally we generate the path. So we need to generate, of course, some path that follows. So here you have another illustration. You have the parameters that we are controlling below. These are painted by hand. And as you can see, we can get interesting effects, for instance, for the design of shoe insoles. We have an ongoing project with the hospital here in NC to design shoe insoles using different materials. And finally, we did some periodic homogenization in 3D. Basically, what we do is we take with different random realizations, and we assess that there is low variance of the homogenized elasticity tensor for linear elasticity. And we see what we saw is that an orthotopic material was a plausible approximation. And here you can see some points of the material space in 3D. So it also covers an interesting space. And here some manifold where we can see the correlation between different parameters. So as you can see, there is a consistent correlation between different parameters and the linear elastic properties of the object. And finally, we did also some very simple uniaxial tests to see if there is a good agreement between the Young moduli. And of course, printing is always introducing anisotropy in the direction. So we also observed some anisotropy in the printing direction with respect to our numerical method. Finally, I'm going to show you some applications. Here, there's a prosthetic finger. What you see onto the right is the actual G-code slicing. So that's why you see this kind of weird image. It's because it's the actual G-code. And here we're controlling the point density on the articulations. And remarkably, you can print that with a fused filament fabrication machine at home. Here you have another application, for instance, a wheel. And here you can see in its glory the concentric field. So as you can see, this is something from a geometric viewpoint, not trivial at all. You have a concentric field, and it's actually varying smoothly and being self-support. And finally, the orthopedic footwear, where you can see the slicing. And here you can see in live 3D printing. So as you can see, we print in a full batch prosthetic hand. And yeah, it prints from our experience, it prints pretty reliable as opposed to other technologies, which means that we can do different hands and always obtain a consistent result. And finally, of course, you can add a skin to the hand to make it less creepy. So if you are interested in trying some of the techniques developed in our team, there is a software that we are actively developing. This is called ISSL. This software is basically a slicer and also has some modeling functionalities. And with this software, you can use some of the infills that I have shown in this presentation. So I would like to thank your attention, and also I will welcome any questions.
Thank you very much, Jonas, for this presentation on the use possibilities of additive manufacturing to create new material behaviors and also functionalized parts. We are a bit late, so just a quick question from the chat from Mr. Wayne. How does the representative elementary volume work when you try to create a geometry that varies in cell site in a particular direction?
So how does the representative volume element?
I think how you manage your homogenization of graded lattice structures, I think.
What's the method we use for homogenization? Right.
The geometry is evolving.
True that. In all the results here, we did homogenization considering homogeneous parameter in the sample. So that's right, that when you finally synthesize a structure at the end, you have spatially varying parameters. So we are not accounting for the variations with the homogenization. But the thing is that we are making an assumption commonly done with homogenization, that is that our structure is sufficiently small in order to get the average behavior. So that's right that, for instance, for more structures that are more like mesoscale structures, maybe the homogenization assumption is not enough, but in our case, it proved all right.
Okay, thank you very much, Jonas, again, for your nice presentation. So now we have a talk of Mr. Vincent Robin from Electricity of France. So Vincent is an expert research engineer on experimental characterization and modelization of manufacturing processes, including additive manufacturing. So today his talk focuses on residual stresses and use during WAM process. Vincent, you have the floor.
Hello, everybody. Can you hear me properly?
Perfect.
Okay, so I will share my presentation. Okay, is it working?
Perfect, you can go.
Okay, well, so first of all, I would like to thank you for for inviting me for this presentation. Then I am pleased to present you the way manufacturing residual stresses issues are achieved in my company thanks to finite element modeling. Yes, this is the content of my presentation. So after a short introduction, I will detail what is computational weld mechanics, which is a field of simulation in mechanics that can be used to address residual stress issues in the industry for high temperature manufacturing on the welding processes. And then I will talk about stress development during process on fitness for service, considering residual stresses, and then it will be time for the conclusion. So the scope of my presentation, sorry, I have just an issue with the Zoom. Okay. So the scope of my presentation concerns modeling of metallic components at solid state, considering continuum mechanics. So we will talk mainly on macroscopic stresses, and we are also interested in some mesoscopic modeling for some specific issue related to intergranular cracking. But for my presentation, I mainly discuss about continuum mechanics approach that are well disseminated and accepted in the industry. So the goal of the presentation is to give you a quick overview of the induced manufacturing residual stress development in some conventional welded assembly, and also for wire arc additive manufacturing components. So I will not talk about powder metallurgy process, but I will say a few words and make some comparison of the approach we have for conventional welding and for wire arc additive manufacturing. So this is the second part of my presentation, which concerns computational weld mechanics, and I just want to detail the approach we have regarding a fusion process like a welding assembly or wire arc additive manufacturing. First of all, we have a competence in for the observation of arc processes, so in situ observation. On this the measurement of this physical quantity is very important in order to get input parameters for the models, but also to check if the results of the model are consistent with the reality. And then sometimes we also need to calibrate the model thanks to some experiments. And that is done using some in-house and open source software like OpenTurns, for instance, which is used to quantify the uncertainty, to calibrate the model, but also to convert physical-based models that are complex to handle with into simplify model like regression or Gaussian process model that are very efficient for decision making. So we can make the difference between two approaches. One approach which is mainly based on fluid mechanics, computational fluid mechanics, that is used to simulate gas flow close to the arc process and also to predict the weld pool behavior. But my presentation, we mainly talk about residual stress in the component, and for this, we mainly use thermometallurgical and mechanical model at the solid states. So if we zoom on this activity, which concerns computational welding mechanics, so we deal with the welding effects in the base metal and in the weld at solid state. And we can address some issue related to temperature cycle through the component to microstructure and also to the evolution of stress and strain distribution. And the approach is mainly based on finite element couplings, coupling to heat transfer, continuum mechanics, and also microstructural evolution that modify mechanical behavior. And most of the approach we develop, because it can be used for engineering purpose, is consistent with some standards related to numerical welding simulation. So just to say a few words about the difference we have in terms of prospects regarding conventional welding on 3D printing with arc and filler metal. First of all, we have two key parameters related to the capability of the model to predict the consequence on the workpiece. The first of all, it's of course the heat source modeling, which is very important to calibrate or to predict in order to have a realistic thermal cycle evolution during the process phase distribution, and also check the homogeneity of the microstructure. And secondly, the mechanical behavior, which may depend on temperature and microstructure, is also important to assess, and it's an important element that can give us information about the risk of cracking during operation, during process operation, and also the effect due to local distortion on permanent result stress and distortion. And if we look at 3D printing using such welding process, we have some other issues. The first issues we have discussed also for powder metallurgy based process, it consists in optimizing the welding trajectory, but also to calibrate the mass transfer and the heat transfer, which is very important to prevent some risk of lack of fusion, for instance. And we have also to define welding trajectory in order to prevent distortions. And finally, but not least, post-treatment on NDT are really an issue regarding this process in order to be able to qualify such a manufactured component. Let's go now to a short description of the way we validate our model in terms of mechanical behavior. We mainly base our approach on Sato-like test. Maybe some of you know this test. It's well known for welding application, and this test is really interesting to reproduce the behavior of the material during successive peak temperature cycle that can be observed in the component during multipass welding or 3D printing. It consists in using a round bar specimen, so it's a uni-axial test. And this round bar specimen is submitted to realistic thermal cycle, fast heating and fast cooling. And we monitor the response of the material in terms of stress, so that we may have the stress evolution of the specimen during heating and during cooling. And the fact that you prevent shrinkage or strained thermal distortion, thermal expansion, then you have compressive stress at heating and tensile stress at cooling. You have here some example of experimental results for two kinds of material. One without phase transformation, which is a nickel-based alloy on the left. So you can see compressive stress at heating and tensile stresses at cooling. And one other with a phase change and volume change due to bainitic or martensitic transformation during cooling. And you can notice that during this transformation, the volume change modifies the stress evolution. And what is interesting is that this Sato test is really is a uniaxial stress. But if you look at the real welding components, when you perform the simulation, you can notice that the stress evolution at some location, for instance, in the heat affected zone, This is the chamfer. This is the added material. This is the tube section of the tube for the base metal. And you can see that the response in stress in the heat affected zone is very similar to the one we have on uniaxial test. Just you can note that this component was used for the industrial measurement of the work of one of the work package of the Brightness 2 project. Sandra Cabeza talked about this project yesterday, and the simulation was used to determine the most relevant position for neutron diffraction measurement on such an industrial components. Second aspect concern also the fact that we are not only interested to residual stresses, but also to the fact that stress developed during the process. And this is an important information regarding some hot cracking issue, for instance. We have developed a specific weldability test for which we can modify the external constraint so that it represents some realistic weld configuration. And you can notice that the behavior in the heat affected zone is always the same: compression at heating, on tensile stress at cooling. But when you apply some extra constraint out of the material, then you can activate the sensibility to the material to hot cracking. You can see in the curve in red that making the constraint higher during cooling leads to a level of stress at the temperature where liquefaction occurs, leading to crack. So this is a way also to calibrate model in order to prevent risk of cracking for welding application. And the other thing is that if you use transient analysis like we do for computational welding mechanics, you can optimize the strategy for weld deposition, reducing distortion, or may sometimes also check to prevent some hot point for residual stresses. So the last part of my presentation before conclusion concern the use of residual state for engineering purpose. And we have been working for a long time. EDF is involved I've been involved for a long time within in-kind contribution project driven by the European Commission, which is called NET project. And this project has for objectives to develop standards for stress modeling and measurements techniques. And within this project, we are working in task group, and the EDF is managing two task groups, one on multipass weld nickel-based alloy, and one other for welding repair on ferritic steel. And so there are still 4 task groups that are very active, and we are mainly working on what we call transposition mockup that are used to validate modeling, but also to give confidence in measurement techniques that sometimes cannot be applied on real components because the components you are interested in are quite heavy and of large dimension. So this is a way we try to develop both experimental techniques on stress modeling for our application. So just quickly some result of 2 task groups that are largely active. And just to give you another view of the quantity, the amount of data that have been collected. And also, for instance, I can show you here the stress, the dual stress through the weld line that have been obtained with different instruments based on neutron diffraction, but also a synchrotron measurement. And the results and the comparisons are really, really good between simulation and measurements. Yes, I would like to say a few words about thickness fitness for service of components, we have to prevent our component from cracking and damage in service can come from brittle fracture, from fatigue, or from corrosion. And we are not only interested in residual stress in the bulk, but also in residual stress on the surface, because generally the welds are machined or submitted to grinding. And that's the reason why we also want to develop some modeling on some diffraction measurement approach that can catch the stress, residual stress close to the surface that may affect the residual stress due to welding. So this is an objective of the new Easy Stretch project starting this year. And the objective we have within this project is to aid the comparison between simulation and measurement results. For instance, gauge volume, reference coupon for D0, elastic constant, and so on. Last slide for this part of my presentation concerns the fact that finally using finite element at the manufacturing stage allow us to have a monolithic finite element approach to submit this component to in-service loads. And some other European projects dedicated to material hygiene have allowed us to demonstrate the break preclusion concept for dissimilar metal welds. It's a very complicated weld component due to the manufacturing process and the choice of the material, because it's a welding between a ferritic steel and authentic stainless steel. And the process is very difficult to apply, but the consequence also is difficult to justify, because we have many materials, and what we have demonstrated in this during this project is that we can couple both manufacturing and in-service analysis to demonstrate the margin we have considering or not residual stresses in for the design of components. So it's time for conclude now. As a conclusion regarding the fact we are interested in wire arc manufacturing, we have a large operating experience in welding and based on the filler metal procurement requirements. That makes wire additive arc manufacturing interested for pressure equipment manufacturing and also repair. The message I will say also is that we need to complete finite element modeling prediction with non-destructive techniques. It is really important to show that model is predictive, and measurement techniques are necessary to make the transposition I was talking about from the mockup to large equipment that cannot be easily produced, and also for which non-destructive methods are quite costly. I will also say that simulation of experiment is necessary to determine key non-observable physical constants. For instance, knowing the level of stress at a specific location during a weldability crack. And also we are working now on monitoring on in-situ measurement, which is relevant to understand the physics, to identify correlation between key process parameters and material processing, and also to define relevant input parameters to have the right level of modeling, and also to collect data for machine learning. Here you have a small movie of what we do for process monitoring. We have developed some automatic weld pull control detection that can be used then for machine learning, coupling with key process parameter like energy and velocity. And finally, I would say that data plus physical models are for us an issue, because we think that it will allow real-time predictions. It will also reduce the uncertainties for decision making, and it's important to have both sources of information to give confidence in simulation expertise. Thank you for your attention.
Thank you very much, Vincent, for this presentation. I have several questions in the chat for you related to fast transformation. You use a strong coupling technique between mechanics and metallurgy. And do you take into account, for example, trip effects in your model?
When you mean trip effect, it's the fact you may have some mixture of cubic phase center on the cubic center material.
In fact, it's the transformation induced plasticity.
Yeah, okay, yes, yes, transformation induced plasticity. Sorry, yes. I have shown you during the volume change of between austenitic steel, from austenitic steel into ferritic steel at cooling for low alloy steel. We have a model which is based on Leblond approach, on which consider induced plasticity. And this model is calibrated thanks to dialectometry test with stresses applied during the test.
Okay, so you have an uncoupled chain in your case.
Yes,
okay.
It's coupled. We describe the plasticity model during the transformation thanks to this Leblond model.
Okay. A question also on computation time. Mm-hmm. I imagine, do you think that your approach of direct weld bed deposition can be applied for large parts? For question purely of computation time?
Yes, that's really an issue regarding regarding the conversion from what we do in welding on what we want to make on 3D printing for large component. The idea is then to maybe use surrogate model or to make some optimization not for the complete part, but for some region of the final component. For the moment, we are working at the scale that can allow us to make 3D complete simulation, but we know that in future we will need to improve this issue regarding computation time.
Okay, and just a last question for you. On the plasticity model you are using, what kind of hardening you are taking into account for each phase in your model?
So the material we are using for most of them are not precipitated hardened material. They are more hardened by strain hardening. So it means that considering nickel-based alloy, nickel-based alloy 600 and 690. So the precipitation does not play a major role on the mechanical behavior of such material. So the model we are using for such alloy is mainly based on a competition between strain hardening and the recovery effect. So there are no really precipitation hardening model. For steel, it's different. For steel, we are using some phenomenologic model that can be based on chemical composition that allow us to simulate what we call CCT under welding conditions. So we have some CCT diagram, continuous cooling transformation diagram, depending on chemical composition. And this is really important to have this dependence on chemical composition for ferritic or low alloy steel assembly, because the carbon equivalent is very different between base metal and filler metal. And this carbon gradients leads to material difference in terms of behavior, but also in terms of hardness and so on.
Okay, it's clear. Thank you very much, Vincent, again for your presentation.
Thank you.
So the last presentation of this workshop deals with European project opportunities. by Jean-Yves Escabas from CIE. So Jean-Yves is a long-time research project manager in different industrial sectors. Since 5 years, he is the coordinator of large European projects at CIE, and today mainly in 3D printing activity. So Jean-Yves, you have the floor.
Okay, thank you, Guillaume, for the introduction. Let me just activate the share modus. So I suppose you see my screen now.
Yeah, okay, we see the screen.
Okay.
Can you please expand? Okay.
Yes.
Nice.
Give me 5 seconds. Okay, thanks. Would like to thank the organizers for the invitation to the WAM workshop. So very high level as regards technology. We're not going to talk very much about technology, more about project management, and this is something that will become a bit more and more difficult, I would say. But let's go through. The plan of my presentation today is to say a few words about Horizon 2020, no more, you see, Horizon Europe. So it has just opened. Not all calls are public yet. We are working with drafts. So regarding the few selected calls, which I will discuss today, they are based on drafts. So I would like to draw your attention on the deadlines, in particular being provisional. I am not expecting the content of the calls to change very much or not at all, but please check the deadlines in the final versions. So as far as I'm informed, the calls in what is of interest for us today will be published 25th of June, so very soon. We will concentrate on two actions. It will be the research and innovation actions, the so-called RIAs. So they are activities to establish new knowledge, so really research to explore feasibility or new improved technology, process, product, as compared to innovation actions, IAs, so activities to produce plans, arrangements, or designs for new products or processes. They differ in content of activities and, of course, in TRLs. So RIAs are start TRLs around 3, end TRLs 5 or 6, and innovation actions will start at 5 and mostly end at 7. We will have a look at a few other multinational funding programs, so MRNet and EIT. So I suppose you all know Horizon Europe. We will concentrate, let me display my pointer. We will concentrate on pillar 2, and more specifically on clusters 4, that's digital, industry and space, and on cluster 5, that's climate, energy and mobility. So what's new in Horizon Europe versus Horizon 2020? Not a lot of things, but significant changes. Now the calls are oriented on outcomes, which is very important. So Horizon 2020 already put a lot of emphasis on the impact of projects. So now, well, the calls just start with outcomes, what the Commission is expecting. And that's basically what I'm going to show you today in those selected calls. Another big change is that the calls are no more focused on technology. They are focused on the outcome. So you will get more liberty to propose technologies to the Commission to fulfill these outcomes. And of course, since they are no more devoted to single technologies, for instance, all calls on manufacturing, they're very open. You can propose additive manufacturing, but also casting or injection molding or whatever. So of course, you will have a lot of proponents. So the competition is going to increase a lot. And of course, the technical challenge will be higher for you because you have really to imagine solutions to fulfill the expected outcome. And in some cases, you will need quite some imagination to fit additive manufacturing in those calls. The proposal template has also changed quite a lot. It's shorter, 45 pages instead of 70 most of the time. So no more space for blah, blah, blah in writing your technical content. You need to go straight to the point. They also have introduced a new approach to the impact with the so-called KIPs, the key impact pathways. But luckily for you, the template in the impact section is quite detailed. So the Commission really tells you what they are expecting. Of course, you have to provide the figures. Yeah? That's not new. So I can say it's quite a paradigm change for you. Writing the proposal, and I'm looking forward to seeing the first proposals or the results of them in this new framework. So the first call I selected, actually I made the selection by decreasing interest for AM, I would say, or this decreasing relevance, you will see. So what we're starting with is quite relevant at the end. You will need more and more imagination, as I said. The first one is a twin transition 1-2, zero defect manufacturing towards zero waste. Twin transition means first digital transition and second the green transition. So all these goals need to cover both aspects in your proposals. So here you will have to demonstrate a significant increase of sustainable production through improved control systems and non-destructive inspection methods, methodology and tools to prevent generation of defects at component level and its propagation to the system level. So you see not only the technology itself, but you have to integrate it to the whole process. You have to create new diagnostic methods for in situ monitoring of industrial production to ensure efficient use of material. So that's the green aspect of the twin transition. So of course, like always, reduce production cost and time. So, I mean, this is a nice call for additive manufacturing, but you have to expect competition from other manufacturing technologies. The second one is the twin transition 1-3, laser-based technologies for green manufacturing. So you see again, the green is here. So the green manufacturing through the application of laser-based technologies in order to improve the agility of industrial production through data exchange. So again, you have both aspects, green and the digital transformation. And you have the indicators improving the environmental sustainability of industrial production. So clearly towards first time right processes with 30% lower consumption of resources compared to state of the art. And as you can consider that, well, AM already belongs to state of the art. This is quite challenging here. You will have to integrate state of the art high power lasers and tailored beams with sensors and real-time monitoring systems. And you will have to do that in 3 use cases. So this call is quite interesting, but quite challenging. Clearly, it's about laser technologies and photonics. You will have to use the digital chain towards the flexible production, and you will have to integrate quality sensors in laser-based manufacturing. So quite challenging. Next one is resilience, still in cluster 4, 114, development of more energy efficient electrically heated catalytic reactors, innovation action, sorry. So quite challenging to achieve TEROL 6. The Commission is expecting a shift from fire to electrically heated catalytic reactor. So clearly to replace fuel heating or gas heating by electrical heating in order to save CO2 emissions. Of course, it requires the redesign of the reactor. So clearly, if you can or must use additive manufacturing here, you will need to do that integrated over the whole design chain of reactors. So you will have to work not only with end users, but really with specialists of reactors. You will have to demonstrate a significant process intensification. So by reducing the size of the reactor, and of course, still with industrial scalability. We are in innovation action, TRL 6. You have to use integrated development methodology of catalysts and reactors for optimized design. And of course, advanced catalytic reactor concepts. So of course, you will be able to propose reactor exchangers. You will have to address corrosion resistance, thermal conductivity, thermal simulation and design. And well, I already said it, you have to co-work with end users, definitely. Next one is different. It's about electric motors. So cluster 5, D5, destination 519, next generation electric vehicle components, high efficiency and low cost electric motors for circularity and low use of rare resources. So it's clearly described in the expected outcome, lower cost, high efficiency and powered electric density electric motors. So that's for cars and vans. Designed to X approach, you will have to address easy dismantling and recyclability through the development of or application of advanced configuration. So that's clearly improved motor design and development processes. You will have to use topology, optimization, operational improvement, and address novel manufacturing process, supporting increased integration, enabling, amongst other things, improved thermal control. So this speaks of electric motor designed for AM. It speaks for complex shapes for magnets, and the improved thermal control calls for cooling channels, for example. So this is clearly for additive manufacturing here, but not for any materials. You will have to address the low use of rare resources. So clearly that's printing permanent magnets. So this is quite challenging. State of the art is already there. We're not starting from scratch. It is still a research innovation action. So you can start with a rather low TRL, provided that you achieve between 5 and 7. So again, something needs to be done with end users and integrators because, well, you have to demonstrate electric motors at the end. Next one is in the space area, again, cluster 4. Low cost, high thrust propulsion from European strategic space launchers. Technology maturation, including ground tests. So we had this introduction talk yesterday by Laurent Pampagian, told you what you could do with additive manufacturing in the field of space technologies. So reducing cost price, which is the major outcome expected by the Commission here, is not always obvious, even with additive manufacturing. Here, it's about maturing, prototyping, and ground tests. So you will have to produce real parts with additive manufacturing. Mature technologies means that you will have to be at 5, 6 in 2 years, 2, 3 years. And ground tests and engine subsystem system level in 5 years. So again, quite a challenge in a research innovation action. So this can address combustion chambers, so high temperature, high pressure, again, internal cooling channels, but you can also address injector systems. Even if this is a RIA here, state of the art is there, and there have been already some publications on this. Next one is on, again, cluster 5, destination 5, next generation of digital aircraft transformation. This is clearly a call for the digital aircraft factory, transformative digital technologies, using multidisciplinary model-based digital twins, enable flexible integration of simulation ecosystems in an extended enterprise context, means that you will have to address both vertical integration and horizontal integration, that is to bind the shop floor to the ERP of the company, but also include your suppliers and customers horizontally. Model-based validation and certification is the real world. So you have to provide for parts allowed to able to fly in the short term. Next call, well, less and less relevant. I told you, resilience 112, functional multi-material components and structure. So the Commission clearly is expecting optimized lightweight designs requiring the use of multi-materials. So that's not straightforward for additive manufacturing. So you have to expect competition by other manufacturing technologies, but still multi-material additive manufacturing, multi-material design for AM are already state-of-the-art. You will have to address all aspects from design to manufacturing, including use and recycling. So that's, again, quite extensive. You have very ambitious targets here, reducing the weight by 50%. So again, the design for AM will help you here compared to other technologies. Reduce the lead time, for multi-material products by 20%. Again, additive manufacturing has a lot of assets here. Increase product performance by at least 30%. And what the Commission is expecting here, the development of ready assembled multifunctional devices here speaks for part simplification. So don't forget that you're allowed to use hybrid manufacturing here, so part additive, part non-additive. Next one is also possible for multi-material additive manufacturing and hybrid manufacturing. This is the Twin Transition 112, products with complex functional surfaces. So the Commission is quoting additive manufacturing among the possible technologies here to develop new surface treatments, specifically targeting and enabling end products. So to reduce energy usage and environmental footprint. So when they say this may include, well, it means that it's recommended to include co-design of product geometry and surface properties. So you will have to integrate the new surface treatments in a manufacturing line for complex shapes or multi-material consent. So again, very challenging, but still an opportunity for additive manufacturing. The last one in Horizon Europe is again, well, relevant for additive manufacturing, clearly, but still challenging. This is Twin Transition 1.7, artificial intelligence for sustainable agile manufacturing. So you have the space here, but clearly you have to implement AI technology in additive manufacturing, integrate in the process to improve the environmental sustainability of industrial production, to improve the agility of the industry, and do that with the aim of improving the sustainability of the sector, advanced circular manufacturing and remanufacturing technologies. So again, quite a challenge here. And of course, again, I'm repeating myself, don't work alone. You have to work in a value chain. So multinational funding doesn't only mean Horizon Europe. There is the European Institute of Innovation and Technology, KICS. So the KICS, so compared to Horizon Europe, which networks you for research, which gives you money to develop knowledge, the KICS network to integrate education, research, and business, and they want to generate impact, produce economic value. So they convert knowledge into products and services in order to introduce the technologies to the market. There are several KICS here, and they have a nice portal. You have this link here, leading you to opportunities for funding. So no opportunities open for the time being, but there are several KICS of interest for AM. This is the KIC Digital, Manufacturing, and Raw Materials, which you can browse to find opportunities in the future. So I just recall you the main rules in KIC funding projects. The goal is really to bring innovations to the market. So you must prove that your innovation will be in the market within 3 years and preferably even earlier. They're mostly intended for KIC members. So if your partners, they don't need to be members of the KIC, but they need to promise to become one during the project. High TRL, clearly, 8 at the end of the project, 9, very briefly, very shortly. Co-funding principle means that you do not get 100% funding like Horizon 2020, more likely would be 70%. Backflow principle means that you have to refund the money afterwards. If your project works, you have to pay back. So you have to introduce in your proposal a backflow plan, which will be evaluated. So if the commission or the EIT, evaluation panel, estimates that it's not credible, you have bind point there. So they want to see their money back. So that's really a drawback. There's also the ERANETs, for instance here, the M ERANET, so M for manufacturing, for modeling, functional materials, additive manufacturing. So there's a call open until the 15th of June for the pre-proposal, so it's feasible still. Just want to recall you what ERANETs are. So they are European networks of funding agencies in the EU. So they were funded into an instrument from FP6, so it's quite old. They were funded as CSAs. They were aimed at fostering transnational collaboration between member states. Now they have been superseded by more modern instruments like Article 185 initiatives, Eureka, or now joint undertakings, but they're still existing. There are still a lot of them active, in particular MRNet. So they have joint calls. The projects are funded nationally, sometimes with additional European funding. And project partners, they are funded by their own funding agencies. For instance, France is BPI or the ADEME. Okay, so I will wish you nice success in your proposals. I'm available for questions now or later for information or networking or whatever. I have a position in the new system of the European Union, which is the Relay Horizon Europe system, where I'm supposed to multiply information. That's what I'm doing today, networking. And thanks again for listening.
Thank you, Jean-Yves, for this landscape view of European calls. It is a good introduction for the discussion groups for this afternoon, for sure. Jean-Yves, just a question. Is it an abuse to say that material research is no more in the scope of European calls, but finally always present because of strong coupling between the non-standard behavior and enhanced functionalization possibility and the industrial application clearly focused by these calls?
Yes, absolutely. You're fully right. As I said in my introduction, the calls now are focused on the expected outcomes. The Commission wants results. They want impact. They tell you, and that's the sign, the call, they start with the outcomes, expected outcomes. They tell you reduce by 30% the use of raw materials in the manufacturing sector. So this is true for AM, this is true for injection molding, this is true for any manufacturing technology. So they just give in the scope a few indication of what is possible or even recommended, but it's not exclusive. And well, there's nothing about materials or specifically about materials. It's specific about, well, how you use the materials to provide products on the market. So the calls will be on material savings rather than on material performance.
Okay, thank you, Jean-Yves. There is no question in the chat actually, so we can close the morning session. Thank you again to all speakers and participants of this workshop, which I hope will take place again in 2 years. Perhaps Caroline or Sandra, you can introduce the discussion group's organization for this afternoon.
Yes, thank you, Guillaume. So this afternoon, we are starting at 2 with 4 discussion groups open. You will be asked to join one of the discussion group for 45 minutes. And afterwards, we will be gathered all together, and then you can then select another discussion group where you can take part. I now let Steph maybe to explain the technical aspects of these meeting sessions.
Yeah, so I'll share with you in the chat the link for this afternoon's meeting, but it will also be sent to you by email, and we'll start the meeting like we did for the webinar, and then each of you will choose the group of discussion you want to join. This will be 2 sessions of 45 minutes, so the breakout room will be merged again after 45 minutes so that you can choose another topic to discuss in the second round. So stay tuned, look at your emails, and we'll see you back tomorrow at 2 p.m. Thank you.
You too. Bye-bye. Bye.
Bye.
Bye-bye. Bye-bye.